In this final formal video where we're going through the background theory, we're going to consider Maxwell's equations and how we can derive them from the electromagnetic field tensor, which I just explained in the previous video. There are two results that we're going to need. The first result is that d beta of f alpha beta, and note that because we've got opposed indices, we're going to be contracting over beta, that's the sum, is equal to mu naught j alpha. I'll prove that in a moment. And then the other one is a slightly more cumbersome expression. We have that df alpha beta by dx. Oopsie, that's all going horribly wrong. By dx upper gamma plus df beta gamma by dx upper alpha plus df gamma alpha by dx beta is equal to 0. So those two are results that you can prove. So let's actually start by seeing how those lead to Maxwell's equations, and then if you're not interested in the details of the proof, then you can just accept those statements and stop watching. If you're wanting to follow it through, then you can follow to the end of the video. So let's take this, this first expression here, which I'm going to label as equation 1, and then this second equation here we're going to say is equation 2. So from 1, if we just consider, let's say the alpha is equal to 1 component, what do we get? Well, we get, if we write it out slightly fully, we get df1 beta by dx beta, which is just df11 by dx1 plus df12 by dx2 plus df13 by dx3 plus df14 by dx4. Now df11 is 0, so that first term is 0, and then we can fill in the dots, so we have dbz by dx, sorry, not dx, dy, x2 is y, minus dby by dz, so f13 is minus by, minus 1 over c squared dex by dt. And that is equal to, I should have been putting that here, mu naught jx. I've asserted that, I will show that later. And if we just gather terms and rewrite that, then what we can see is that the left-hand side is just the x component of curl b minus 1 over c squared de by dt. That's the x component, and that's equal to mu naught jx, which is, of course, the Ampere-Maxwell equation. That's the x component of the Ampere-Maxwell. Obviously, alpha is equal to 2 gives us the y component, and alpha is equal to 3 gives us the z component. So equation 1, this simple statement up here, which itself is obviously going to be invariant between reference frames, leads to the Ampere-Maxwell equation. Oh dear me, I did not mean to do that. Leads to the Ampere-Maxwell equation. What happens if we set alpha equal to 4? We expect to find something different here because we're now considering the time-like component. In the source term, that is the charge current density, then we're going to end up with a charge density, so that should give us a clue. So what we find is that df4 beta by dx beta, and I'm not going to write out the individual terms this time, just to save time. It's going to be 1 over c dex by dx plus 1 over c dey by dy plus 1 over c dez by dz, that's rather easy to do, plus 0, because that's the f44 term, and that's going to equal mu naught and then c rho, because remember the fourth component, the charge density component, is c times rho. Of course, what we have there in these terms is just a divergence. So that tells us that 1 over c times the divergence of E is equal to mu naught c rho. If we multiply through by c, and remember that c squared is 1 over epsilon naught mu naught, then we see, of course, that the divergence of E is equal to rho over epsilon naught. And this, of course, is Gauss's law. So that's the two of Maxwell's equations with sources derived from our first equation, one which has a source term in it. So we've got this part has given us Ampere, Maxwell and Gauss. This second equation has 0 on the right hand side, so we might well expect that we're going to get the two Maxwell equations which have 0 on the right hand side. So let's see what happens there. We're going to start by noting that in equation 2 there are all sorts of possibilities for the alphas and betas, but there are going to be two that we consider which are the only significant ones. So first of all, we note that we have to have all indices different, otherwise we don't get anything other than 0 equals 0. So all indices must be different, so we can either have alpha equals 1, beta equals 2, gamma equals 3, i.e. all space-like, or of course permutations, or we can have, let's say, alpha equals 4, beta equals 1, gamma equals 2, and again permutations. And those are going to give us two different sets of equations. So let's start with the first. Let's start with, let's say, df12 by dx3 plus df23 by dx1 plus df31 by dx2, which is equal to 0. And that, of course, tells us that dbz by dz plus dbx by dx plus dby by dy is equal to 0, or div b is equal to 0. In other words, there are no monopoles. Any other permutation of alpha equals 1, beta equals 2, gamma equals 3 will give you the same equation. So that's there's quite a lot of redundancy there. Now let's think about the other form, where we're setting alpha as 4, beta as 1, gamma as 2. And we see that df41 by dx2 plus df12 by dx4 plus df24 by dx1 must equal 0, and that gives us 1 over c dex by dy plus 1 over c dbz by dt, not plus, minus dey, sorry, I've missed out of 1 over c, let me rewrite that, 1 over c dey by dx is equal to 0, which is 1 over c into dex by dy minus dey by dx plus dbz by dt is equal to 0, and that, of course, is the x component of the curl of E plus dB by dt is equal to 0. So this is Faraday's law. And we get the other components just by playing around with the other two indices. So we've now seen that by starting with these two statements, which I haven't yet proved but I will, d beta f alpha beta is mu naught j alpha, and then df alpha beta by dx gamma and permutations equals 0, we can derive all four of Maxwell's equations, which shows that these are a set of equations that apply in all reference frames. So we've reframed electromagnetism in terms of the fields in a way where we can transform between frames. So let me now go back just briefly and prove those two statements. If you're not interested in the mathematical details, you're very welcome to stop the video at this point. We're going to write d beta of f alpha beta. And I want to write out all of the components and find out what that is. So we have df alpha beta by dx upper beta. And that's then going to equal d by dx beta into dA beta by dx lower alpha minus dA upper alpha by dx lower beta. I'm just going to pause briefly and note that what we have is, so out here we have a differential with respect to a contravariant position, so this is going to be covariant, so we'll be able to contract this term with this alpha beta, this a beta. When we think about the other side, we've got a d by dx upper beta and a d by dx lower beta, so we'll be able to contract those two terms. So let's do that, let's multiply that out, and we'll see that we have d by dx beta, dA beta by dx alpha, minus d by dx beta, dA alpha by dx beta. I'm now going to just swap the order of these two terms. Let me get rid of that, go away. Actually, I just need to rewrite that x because it doesn't look much like an x. So that's now equal to the following. We have d by dx alpha, dA beta by dx beta, minus, and I'm going to put these two together, d by dx upper beta, d by dx lower beta, acting on a upper alpha. So what are we going to do with this? Well, first of all, notice that this fellow is d lower beta a upper beta, because remember that when you take a differential with respect to a contravariant variable, you get a covariant differential. And now we have opposed indices, we now have opposed indices, lower beta, upper beta, and of course this is equal to 0 because it's the Lorentz gauge, which is what we use to derive all of these equations. This here is d beta, which we've defined as box. So when we put all of that together, we get the following. We get that d lower beta of f upper alpha beta is equal to minus box of a upper alpha, which is mu naught j alpha, as I stated. That's the first term, the first result. The second result is really just a case of permuting differentials, but there's a slightly subtle point. So we have df alpha beta by dx gamma plus df beta gamma by dx alpha plus df gamma alpha by dx beta is equal to 0. Well, okay, let's not say it's equal to 0, let's find out what it is. We know it's going to be 0 because I've told you. So let's multiply this out. We get d by dx gamma into dA upper beta by dx lower alpha minus dA upper alpha by dx lower beta. We have d by dx upper alpha into dA gamma by dx beta minus dA beta by dx gamma. And notice you need to keep track of which is upper and which is lower, plus d by dx beta into dA alpha by dx gamma minus dA gamma by dx alpha. Okay, so now let's just start gathering terms. We'll notice first of all that we've got an alpha here, an A alpha and an A alpha. We've got a beta and a gamma, and we've got a minus sign and a plus sign. So that's looking quite hopeful. So if I make that term 1, and I'm going to make that term 2, we can't quite say that they cancel yet. So term 1 is d by dx upper gamma. There's a minus sign out the front. Let me just shift that. Minus d by dx gamma of dA alpha by dx beta. Term 2 is d by dx upper beta dA alpha by dx lower gamma. Those look like they should cancel, but notice that there's a slight problem with the indices. In term 1, the gamma is raised, in term 2 it's lowered, and vice versa. But that's okay. These do cancel because if gamma is, let's say, the time-like component in both cases, when we swap them around, we'll get a minus sign in each term, and therefore they'll still cancel. Similarly, beta, therefore we can say comfortably that they cancel. You just have to be a little bit careful when doing that. So 1 and 2 cancel. If I say that this term here with the alpha beta is 3, then there's another alpha beta over here, which is 4, though my beta has got a little bit squashed, so let me just redraw that. And those two will cancel for the same reason that we had before, and then this term here with gamma and this term here with gamma cancel as well. So we will say that 3 and 4 cancel, and 5 and 6 cancel. And so we have the result that I stated, which is that df alpha beta by dx gamma plus df beta gamma by dx alpha plus df gamma alpha by dx beta is equal to 0. So that's pretty much the end of the formal results that we're interested in for the fields. So we started by thinking about electromagnetism and special relativity in general. We looked at 4 vectors, we've looked at the potential, we've now looked at the fields. In the final video, I'll go over some simple examples of how we transform between reference frames.